Welcome everybody. Today's lesson is a little bit different. I'm going to tell you a story about a project I worked on when I was employed at Wisjeni Elsner Associates. Now, Wisjeni Elsner Associates is a firm headquartered in Northbrook, Illinois, and they look at construction materials and buildings and bridges, and they looked at new construction, but we did a lot of failure analysis. So if a bridge collapsed or a building collapsed or there was something wrong with the road or paint was peeling off the wall, they would hire us to find out what the problem was. If it was a design problem, they would look to the architects. If it was an engineering problem, a load problem, they would call the engineers in. And if it was a material problem, they would call the chemists and geologists in. So this is a project I worked on. These were famous walrus heads that were on the side of a building in Seattle called the Arctic Building. And these walrus heads were all around the building, and they were made of terracotta, and they were an important historical feature in Seattle, Illinois. They called us in because there was a failure of the walrus heads. And so as you can see, the one on the left is really cracked up while the one on the right is not. Unfortunately, this is not the before and after. So the cracked one was not the before and the right one was not the after. The problem was the one walrus head that's all cracked up was after they did the repair, and the one on the right was before they did the repair. And that's because they didn't call me in sooner, because as soon as I saw this, I knew exactly what was wrong, and I'm going to tell you about it. So before, they did not like this. The walrus heads were pulling away from the side of the building. And see this metal strap here? It was holding the walrus head onto the wall. They didn't like this metal strap, so they hired somebody else. They didn't hire me, which they should have. They didn't hire Wisjeni Elsner. They hired another firm, and the way they secured the walrus head to the building was they filled the walrus heads, which were hollow, with a cement material, and they put a bolt in the back of the walrus head and used the cement to hold the bolt to the walrus head, and then they screwed it into the wall. Unfortunately, they used the wrong cementitious material because it expanded and it cracked. So the problem with the material that they put inside this walrus head was when it got exposed to water, it expanded and then cracked up all these walrus heads. So then here are the repairs. So you can see this walrus head is really cracked up, and then they used duct tape. And they don't want it to fall on the people below, so they screened it in. Most of the walrus heads could not be repaired, and so they had to make new plastic ones, which were not original to the building, and here they are replacing it with a plastic walrus head. So what went wrong? Well, I said I knew what went wrong because I was very familiar with this. There are some cementitious materials that harden very quickly, and some people use them. They harden quickly. So what's wrong with that? They use something called calcium sulfate, which you might have heard of if you're into art. It's plaster of Paris, calcium sulfate. They add it to cement, but cement is highly regulated in the amount of calcium sulfate that's allowed to be used in them. So when they add this extra calcium sulfate, it causes a problem because after the material hardens, if it gets wet after that time, so after it's all hard and it gets wet like it might get in Seattle, which rains a whole lot. So if this product gets wet after the fact, the water actually reacts with the material and it forms this compound called ettringite. And I'm going to pause the video here for a second, and if you can look at that formula and see what's odd about it. So did you guess what's odd about it? Yes, it has crazy amounts of water or crazy amounts of oxygen and hydrogen, which is from the water. So it has 64 hydrogens. We've never had formulas with 64 of anything, or 50 oxygens. So all that extra rainwater actually becomes part of the product. And so the product grows, and as it grows, it pushes on things, and it pushed and cracked the walrus heads from the inside. So now we had to take the sample in the lab, even though I knew what went wrong, to prove that was actually the case. So what did we do? We asked the people to send us samples. And when they sent us samples, we ground it up. So they took the inside of the walrus heads, the sample of cementitious material, and they ground it up to a powder. And we knew if it had more than 5.4% calcium sulfate in the cement, it was going to be bad. And if it had less than 5.4%, then it was good. My guess was that it was going to be a bad cement. So what did we do after the fact? Well, we took the cement that was all ground up and we added hydrochloric acid to dissolve it, because we can't add water to it because water and cement would make it harden. So we added hydrochloric acid to it. And when we did that, the calcium sulfate became aqueous because it is soluble in water and soluble in acid. So now, instead of having dry cement where I can't pick out the calcium sulfate, I dissolved it and I have aqueous cementitious material in here. And I know from my solubility charts that I could add barium chloride and get a precipitate. So here in the lab at Wisjani Elsner, I did a double replacement reaction just like we did in the class. But instead of just looking to see if it got cloudy and knowing that it had calcium sulfate in it, we actually then collected the barium sulfate to do some math with it. So here's the double replacement reaction that I actually did in the lab. The calcium sulfate was in the cement. We made it aqueous. We added some barium chloride, just like we would have done in the lab. It became cloudy, which meant that we made the barium sulfate, and I have calcium chloride aqueous still. So then I can separate the barium sulfate because the rest is aqueous and I have this barium sulfate. So I filtered it and collected the solid parts, and the aqueous part went straight through. Then when we were done collecting it in a filter paper, we put it inside a crucible. And then there's something called ashless filter paper. So when you put it over a Bunsen burner, you can burn off the paper. So then you're just left with the barium sulfate in the inside. So here's a crucible with the barium sulfate inside. So after that, you can take it to a balance. These were some really fancy balances that I had at Wisjani Elsner. And you can measure the amount of barium sulfate and then calculate how much calcium sulfate was there. So we did all the problems that like you're doing in class. I did it on a regular basis at Wisjani Elsner. And sure enough, we found out that they used a cement that had way too much calcium sulfate in it, which made it set faster, but made it susceptible to expansion if it got wet, which is the what likely happened in Seattle, which rains a lot. And so then we solved the mystery and unfortunately couldn't fix the walrus heads, but they did get some money from the people who used the wrong cement on their project. If they had asked me first, I could have told them, don't use this because it's going to be a problem. So that's a little story from my work at Wisjani Elsner. Hope you enjoyed it.